All right, so this is video number 2 on annuities. In this video, I'm going to go over questions where we are determining the present value when payments or deposits are made at regular intervals. All right, so this could be you're taking out a loan today, you're borrowing money today to pay for a big ticket item like a car or a house, and you're going to be paying it off gradually with regular payments. That's kind of the most common one. And we'll look at a couple of other scenarios too. Okay, so the present value of an annuity is the lump sum that has to be invested today to provide equal payments or withdrawals at regular intervals over a specified amount of time. So that's wordy. I'm going to explain using that timeline underneath. The present value of an annuity is also, or it could also be, the amount borrowed that's going to be paid off in equal amounts, like the mortgage. Okay, so there's two kind of different scenarios. In the second one, that's where you're borrowing money to buy something. And then the first, like the one at the top of the page, or the top of the slide there, that's like you're depositing money so that you can have money later that you know you're going to want to take out, like a savings plan. So in the timeline at the bottom of the screen, this time the arrows all point to the left. The idea is that this side is before, and then the right is like after, or like sooner and later in the timeline. After. So in year 0, nothing's happening. But at the end of year 1, I want to be able to withdraw $1,000. So I'm hoping I can withdraw $1,000 every year or every month or something like that. In order for the $1,000 to be there, I must have deposited a principal amount of $952.38 in order for it to grow to the $1,000 by the end of the year. All right, in order to have another $1,000 ready by the end of year 2, I need to deposit $907 today, and over the 2 years, that one will grow to be 1,000. To get ready for the third withdrawal of $1,000, I'm going to deposit 863 today, and that's going to have 3 years to grow, which is why it's less money. And these numbers go down and down and down. The longer the money's sitting in the bank, the more interest it can earn. If we add all of these principal amounts or present values together, we can find the present value of the whole annuity. So this one, it looks like we want $1,000 per year for 5 years. That's what we're hoping to have available. So maybe this is like through university or something like that. Like you're planning on having some regular money available. We can plan for that and get ready for that by depositing this present value on day 0. Okay, so we put this money in the bank now, and then every year for the next 5 years, I know there's going to be $1,000 available to me to withdraw. Okay, so it looks like $600 or $700 extra in interest if we compare that to the 5,000 that we're going to be withdrawing. Okay, so that's kind of the idea behind this type of question. The formulas here are pretty similar to the future value ones in the previous video, except instead of future value, we see PV for present value. You can also think of that like the principal or the beginning amount of money. Again, we see R for a regular payment or withdrawal. Sometimes we'll also see payment, PMT, in that spot. There's an interest rate, which is like the annual interest rate adjusted based on how it's compounded, so monthly, quarterly, weekly, that kind of thing. N, again, is the number of payments or withdrawals in total, so we can figure that out. On the right side, there's the rearranged version of the equation. where you know the present value and you can figure out from that what the regular payments or withdrawals are going to be able to be. Alrighty, so one thing just to make note of here in both of these equations, um, the exponent is negative n, so we're going to be careful to put it properly together in our equation with a negative sign. All right, so example 1. Joan sponsors a scholarship in memory of a loved one at her university. She wants to deposit money into an account now so that $1,000 can be withdrawn each year for the next 6 years. So this story is like very similar to what that timeline was on the previous slide. This is for 6 years though. The annual interest rate is 5% per annum, compounded annually, so no adjustments need to be made. How much does Joan need to deposit to set up the scholarship? So how much does she have to put in now? That's her present value that we don't know. She's hoping to have $1,000 available every year for 6 years. So that's the regular part of this scenario. The timeline there is 6 years, and it's compounded annually, so I don't have to multiply by anything. It's just 6. And what am I missing here? The interest rate, 5%, changed into a decimal, 0.05. Okay, so the version of that formula that solves for present value is the one on the left side of the screen. And it looks like R and then the square bracket, 1 minus 1 plus I to the minus n, all divided by I. So it's a very similar equation. You might notice the order of the subtraction is different. In the previous video for future value, the power came first and then take away 1, and the sign of the exponent was different. So a couple of little changes here. I'm going to do the substitutions. So the regular deposit or the regular withdrawal that's going to be made is $1,000 every year. The interest rate was 5%, and the exponent is -6 for the 6 years. The interest rate was 0.05. So this one we need to be careful with the calculator. I showed one question where I did the coefficients, like everything except the square bracket first, and I like to do that again. 1,000 divided by 0.05, that's 20,000. And then the square bracket, 1 minus 1.05 to the exponent -6. You can do all that in your calculator in one step, and the answer should come out to be 0.2537846. And we need to multiply that answer by 20,000. Final answer is $5,075.69. Okay, so today Joan can put this 5,075.69 in the bank, and that will set things up. Since it's going to be growing interest, that will be set up so that every year $1,000 can be withdrawn for 6 years before the money runs out. Okay, next one. Example 2. Rob bought a snowblower for $1,500 and he financed it at the store. So you probably have heard commercials about finance rates and stuff like that. Low financing and those kind of phrases. Or 0% financing, which is very nice. But he bought a snowblower for $1,500, financed it at the store, meaning the store loans him the money and he pays it off gradually over time. He's going to make weekly payments for 60 weeks, which is, I think, 5 years. If you do that divided by 12. Oh, 60 weeks. I'm thinking months. Anyway, so we can figure out what that is. It's just over a year. And the loan has an interest rate of 7.5% compounded weekly. All right, so here are our details, and we're trying to find out the weekly payment. So we don't know the regular payment in this one. The present value is the cost of the snowblower that he's buying today. And today it costs $1,500. So he's going to get the snowblower, which is worth $1,500, and he's going to gradually pay it off. The interest rate, 7.5%, so 0.075. Compounded weekly means we split it into 52 little chunks. I'm going to have to round this one off because it's like a long decimal number, but it's 0.00144 roughly. And then we still have to find the number of payments. It's actually just those 60 weeks. Okay, so all the planning is done. We can set up the formula. So this time we're looking for the weekly payment or the regular payment. So we're using the other formula, the one from the right-hand side of your handout or the slides. Present value multiplied by the interest rate. If you want brackets or something to remind you you're multiplying, you can do that. 1 minus 1 plus I to the exponent negative n. Substituting all the known values, 1,500 times 0.00144 divided by 1 minus 1.00144 to the negative 60. Again, careful to make sure we're using a negative exponent. That's important. With my calculator, I'm going to multiply the two numbers in the numerator together to get 2.1634615. The denominator, I'm going to do all in one big step. So 1 takeaway, 1.00144 raised to the exponent negative 60. That denominator should come out to 0.082842. And then doing that division, we can get our final answer, which is 2612. Okay, so Rob gets his snowblower today, and rather than paying the $1,500 right away, he's going to pay $26.12 every week for 60 weeks. I think that ends up being $1,567. I think I worked out before in total. So definitely more than the cost of the snowblower because of the interest. All right, there's one last example. This one we have Gru. He needs to purchase a new vehicle. He and the minions can afford monthly payments of $700 for a maximum of 10 years. The best interest rate he can find is 6.3%. 0.063 compounded monthly. How much can he buy the vehicle for now? Okay, so like which vehicle could he afford is another way of saying that. All right, so I jotted down some of that stuff as I was reading it. The interest rate comes out to 0.00525. The number of payments, so it's 10 years and then 12 payments per year. So 120 payments he's going to be making. And this time, Gru needs to know his present value. R times 1 minus 1 plus I to the minus n divided by I. Point 0.00525 to the negative 120, all divided by 0.00525. Sorry, just shifting my slide around there to make it bigger. Okay, so this is one of those ones where I like to do the non-square bracket stuff first. 700 divided by 0.00525. That's 133,333 and a third. So I'll keep the 0.3. This square bracket, all of that is going to be typed in one big step. One take away the base to the exponent negative 120. And the answer I get for that part is 0.466529,772. So again, I'm not really sure how many decimals I need to keep to make sure this is accurate, so I'm just keeping a bunch. And then we're going to multiply those two numbers together to get $62,203.97. Okay, so that's what he can afford. Like on the day he's buying his car, he can look at a car that costs this much money and know that he'll be able to afford paying it off. I think, yeah, so that's it for this last annuity lesson. There is going to be one more video that's going to walk through how to use websites, like an online solver, to do some of these calculations for us. Okay, so in the real world, most people don't sit down and do these calculations like this on paper. Um, they would type all those given numbers in and let a computer or a calculator tell them the answers. So we'll look at that in the last video, and then there's the optional assignment for the afternoon. As always, let me know if you have questions, and join the help session if you do need some help.